I would like to introduce Salim Bhatti, who will be presenting End System Controlled Dynamic Multihoming and Multipath Transport. Salim is a professor in the School of Computer Science at the University of St Andrews and traveled from Scotland, UK to join us today. This is Salim's second time presenting a NANOG. Salim's first talk at NANOG was called ILNP, a Whirlwind Tour, a NANOG 50 in Atlanta in the year 2010. Welcome, Salim.
Thank you very much. Thanks. Which one's the advanced on here? Good morning to you. I'm very grateful to be presenting here, a different kind of talk for you just before lunch. This is part of an ongoing research project that I've been involved in for a number of years. And these are just some recent results that I will present to you from November last year as part of the ITF hackathon, looking at a new protocol for the network layer. I'm currently working with Rod Grimes and Alistair Woodman with support from the ICANN grant program, and a special thank you to Con Riley and the ITF NOC team for the connectivity that was needed to give me the results that I'll share with you at the end of this talk. Okay, so straight down to it, what is the problem I'm trying to solve? So as part of my wider research, I've been looking at a new network architecture that hopefully is simpler and can combine some of the core functionality we need to do things such as provide some sort of support for multiple network paths to be used in various application areas through applications. So for things like load distribution or load balancing, graceful failover, resilience for not just for individual nodes, but for sites, support for mobility, both mobile nodes and mobile networks, but also give benefits potentially for security and privacy by being able to scatter packets across multiple paths. The applications access this through a transport protocol, of course, and there are some options available. SCTP and Multipath TCP are fairly mature and they have their uses, but they haven't really had much uptake. Quick Multipath is still work in progress, and maybe that will encourage people to use Multipath more. So the question I'm really trying to ask myself is there a more general capability that can be provided lower down at the network layer that can be used by multiple transport protocols for multipath operation? And is that something that can even be applied to existing protocols like TCP and UDP for the benefit of existing applications? Okay, so how have I gone about this? As I said, this is part of a longer research protocol. Some research work looking at a protocol called the Identifier Locator Network Protocol. And this is providing capability that hopefully is enabled in a simpler way, giving you a simpler kind of engineering landscape, less complexity than we have now, by not having to deal with tunnels or proxies, no network address translation, but does work over existing infrastructure and for existing applications. And it's based on taking a completely end-to-end approach and doing something different with addressing, which I will jump straight into. So to look at how addressing is different in ILNP, let's compare it with what happens in IP version 6. In fact, the protocol is being built on IP version 6, and certainly you can see it as an extension to IP version 6 or a superset of IP version 6, but you'll see there are some differences. So here is the IP version 6 address structure taken straight from RFC 8200. And below that is the ILNP way of doing addressing, which is to use an identifier locator vector. Why is this different? Well, firstly, to distinguish it, but in fact, there are some similarities. So first of all, it's the same size as an IP version 6 address, and some parts of it are very similar. In fact, the locator, which is a topological locator, effectively this is a label for a network, that is pretty much an IPv6 prefix. And that's really useful because if it's the same as a prefix, you keep IPv6 routers happy. So my ILNP packets should make their way across an IPv6 network just fine, because the routers are happy that they've got a label for a source network and a destination network, so packets can go across the network just fine. The lower 64 bits, however, are treated in a very different way. In IP version 6, they're effectively an interface identifier, and in ILNP, they become a node identifier. They're not bound to an individual interface, they're actually bound to the node as a whole, and I'll give you more information about how they're used. In terms of how this is viewed in packets, as the packets go across the network, well, as far as an IPv6 router is concerned, the yellow parts there aren't changed at all, and those are the bits that an IPv6 router cares about, so those packets should get across the network just fine. Then on the right-hand side, the shaded areas are the ones that I get to play around with in the end systems only. So that's the structure of the packet that the end system sees, and we'll see how that's used in the next few slides. Okay, so I'm kind of coming bottom up. What does this mean for how addressing is used in the protocol stack? So here is the kind of thing we have today with IP addresses. An IP address is assigned to an interface on a machine. It's used at the network layer. Full IPv6 addresses are used as part of the state at the transport layer. So TCP uses the source and destination address. And of course, the address is available. You could, if you wanted to, use it as part of the application state for an application session. But what that does mean is that at the very least, your transport layer flow is tied to a particular network and in fact to a particular interface on the machine it's going out from, and therefore doing things like multipath, where you might have to use multiple addresses, becomes a little tricky. And same with if you want to do things like mobility, that becomes a little tricky because you're going to move across networks and possibly move your flow across interfaces. So the model for addressing in ILNP is different. So if we start at the transport layer, you don't use the whole of the IPv6 address, you only use this node identifier. And that stays stable for the duration of the transport layer flow, and it's not used at all at the network layer. At the network layer, you have this locator. Remember, that's just an IPv6 prefix. And then the operating system at the end system, that just keeps a log of the bindings that exist between a node identifier and a locator. And those mappings, those bindings can be one-to-many. So you can have an identifier that is bound to more than one locator, which means it's attached to more than one network. And so your transport layer flow can be distributed across more than one network. And then the locator has a dynamic binding to an interface. And for practical purposes, that's pretty easy. In IP version 6, you see a routing advertisement come in on a particular interface. It has a prefix. And so you have a dynamic binding from the locator to the interface. And that is valid as long as the routing advertisement says it is. So you have these dynamic bindings, and you have this different form of applying addressing at different points in the protocol stack. How does this look like at the transport layer? So here's a very simplified diagram of two nodes communicating. In IP version 6, they have addresses assigned to them. Nodes X and Y have addresses AX and AY. And if you were to look at the state for TCP, you would see that both addresses, all the bits of both addresses, are used for TCP, and they are bound in a very fixed way to a particular network at the IP layer. With ILNP, that changes. So you have an identifier, a node identifier, that remains stable for the duration of a transport layer flow, but in fact, you can generate ephemeral identifier values. Okay, that's a separate talk, but that's actually very useful for privacy. And then at the network layer, you have these locators, these labels for networks, and you have this dynamic binding between the identifier and the locator. So the transport layer state for ILNP looks different. At the transport layer, you only have the identifier as part of the state at the transport layer, and then you have dynamic bindings to one or more locators, one or more local networks and one or more remote networks. On here, on this slide, you only see one local network and one remote network, but you'll see later on you can have multiple networks, and that will be visible in the results I'll show you later from the testing we did at IETF. Okay, so we need a couple of more protocol elements to make this work, and the first one is a destination option header in IP version 6. That's what that option header looks like. It's a very small header. It has two purposes. The first purpose is to distinguish the packet carrying this destination option header as an ILNP packet to the receiver rather than an IPv6 packet. The second thing it does is it contains a pseudo-random value, a 32-bit value, the nonce, and that acts as a way of protection against certain off-path attacks, and also effectively becomes logically a part of the transport layer state. And it just gives it a little bit of extra entropy for distinguishing that transport endpoint from any other one. Okay, so that's what's happening at the transport layer. And as I've said, you have this dynamic binding to the network layer. The other protocol element that we need is a way for one node, when it has a change in its locators, to notify the other nodes it's talking to what its new locator set is. And that's done through an ICMP message, and it's called a locator update. It's a very simple handshake. When node A has a change in its set of locators, it creates a locator update message. It puts into that message its new set of locators. It sends that to the node it's communicating with. The node says, yes, thank you, I've got that, sends an ACK back, and you have synchronization of the new set of locators for that flow, and the flow can continue. Okay, so that's the theory behind it. There's a lot going on, but it's all in the end system. Nothing really needs to change in the network. So can we make this work? We've certainly got it working in the lab, in my test bed back in Scotland. But what I really wanted to do was see how this works over the public internet, because things can change there compared to a test bed. So there was an experiment we ran at IETF 124 in Montreal last year in November, and we ran some tests, from that network at the hackathon back to my lab in St Andrews in Scotland. And the experiment consisted of two tests. The objective was just to see if that signaling would work. Would the ILNP packets get through the network, and would the handshake work in order for the locators to change and for the multipath to work? So the two test scenarios we had, one was a very, very simple TCP level scenario, just using iPerf to generate TCP flows. And this was for normal default TCP in FreeBSD. FreeBSD is where we did the implementation, and the default in FreeBSD 14 for TCP is just TCP cubic. The second scenario we had, it was an application level scenario, and it's video streaming using Dash. This is just using the reference Dash client. And this was a scenario that was chosen because it's going to be a bit of a challenging one. Dash has its own application layer feedback control loop for video, and you'll see that when I show you the baseline results for the streaming. And so it doesn't necessarily know what's happening at the TCP layer or below, especially when things are changing underneath, when connectivity is changing. The other interesting thing to note about this particular experiment is that we used iPerf, as I've already said, for the video streaming. We used Nginx as the server and Firefox as the client. And all of those were standard binaries, no need to re-engineer, no need to recompile. They were just taken straight from the online repositories for FreeBSD and used directly. Now, our code base in FreeBSD 14 is still under development, so we expected a few surprises. Luckily, there weren't that many surprises when we ran the testing, and the preliminary results looked pretty good. Just a quick couple of photographs to show you the kind of setup we had. Nothing special, really. These were the two setups that I was using at IETF 124 in Montreal. The one on the left just had a wireless demo, but the one that you'll see the results for are come from the photograph on the right. And in fact, the interesting part, I haven't taken a very good photograph. It's in a little 4U rack just between that big ILMP poster and the little screen on the right. There's just a little 4U rack there. It's got two workstations, standard desktop workstations, in which I've squeezed in a quad NIC, gigabit Ethernet ×4, into a little desktop arrangement. It's got a little router in there and a desktop switch as well. And it's all pretty standard equipment. In fact, I got that all from eBay just to travel with. And so there's nothing special about the equipment required. In terms of the configuration at the network level, again, pretty simple. We were using 4-way multi-homing at both ends of the network. So at St Andrews in my lab, we had 4 prefixes, and the highlighted values there, 31 to 34, are just the values to look out for in the graphs coming up. That shows the 4 prefixes that we used on different interfaces. So we assigned each of those prefixes to a different interface. And then, as you'll see, I had a script running that just turned the interfaces on and off to basically enable and disable connectivity to the network. At the IETF side, very similar thing. We were given a subnetwork, which we split up into separate /64s, and those have values EEE1 to EEE4, and again, you'll see that on the graphs coming up. And so we took it in turns to send flows from each direction, and you'll see that on the graph. So I haven't got all of the results here, I've just got a summary of what can be seen. So first of all, the TCP results, just basic TCP. Let me just explain what you're seeing here. You see 5 graphs up there on the screen. Along the horizontal axis is time in seconds. And then on the top 4 graphs are the throughputs that were seen, the data rates taken from the PCAP files using some analysis with T-Shark on each of the different prefixes, so on each of the different interfaces. And on the bottom graph is the aggregate throughput that's seen at the receiver. So basically, the flow starts off running on one interface, on one prefix, then another interface is turned on, and deliberately 2 interfaces are kept on for a short time, for about 5 or 6 seconds, and then the first interface is turned off, and the flow has transferred totally across to that second interface. Then we do a similar thing with a third interface. We turn that on, keep that on for a short amount of time, and then turn off the second interface, and so on. So you can see that flow is migrating across the network. Effectively, it's a mobile flow, but also it's multi-homed at the times when you have 2 interfaces on at the same time. And so it can be multi-homed and mobile. In fact, in ILMP, mobility and multi-homing are effectively a duality. And it means you can also have at the network layer a soft handoff capability. So even if your lower layers, your link layer or your PHY, does not support soft handoff, which of course Ethernet really doesn't, you can still do that at the network layer, and this reduces packet loss for the higher layers. Okay, so that was one particular pattern of multi-homing. Here's another pattern of multi-homing. This is more akin to a load distribution scenario. So again, we start off with the flow on a single interface, then we go and turn on a second interface, and you see the load being shared across both of them, then a third, the load being shared across all 3, and then a fourth, the load being shared across all 4. And then, of course, you turn off the interfaces one by one, and you see that the load goes back to a single interface. That little hiccup at around, let's say, 7 or 8 seconds is just a reminder to me, if nothing else, that we're running this on the IETF hackathon network, hundreds of other users, plus we don't know and we have no control over what's happening between Montreal and St Andrews when this is running. So TCP congestion control can cut in. And of course, iPerf has its own behavior for how it does transmission, and you can see that as well. That's the little hiccup there, but that's just to say everything else, iPerf, TCP, are running as they should, and you still have the multipath capability. Okay, so that's the plain TCP results. Let's have a look at the video. And here is just a quick screenshot from the client that was running at the ITF. And what you'll see on the graphs coming up don't show you what I can't even show you in this still screenshot, of course, is that the video playback was smooth. That was Dash doing its job. And so even when you see the multipath and you see what doesn't look like a very smooth line, the playout at the client side was pretty smooth. First of all, a baseline. This is what the streaming of that video, it's a short video, about 3.5 minutes. That's what it looks like when streamed across a single link, a single path rather. And this is typical Dash behavior. You get a burst of packets at the beginning so that the receive buffer can be filled up for smooth playout. And then you get intermittent chunks of video delivered to the receiver so that the playout can remain smooth. So this is what it looks like when you switch on the multipath pattern, very similar to the first one I showed you for TCP. You see that the flow does migrate across the different interfaces, the different prefixes. The pattern of transmission doesn't look so smooth. As I said, the playout was still smooth. Dash was still doing its job. And in fact, what you see there is that each time the flow moves to a different network connectivity, Dash thinks it's starting up again. It sends an extra little burst of packets to make sure the playout buffer is full at the receiver and the playout was smooth. Okay, so that's just a little flavor of what I've been doing with this research. If you want to know more about ILMP, lots more on the website, please do come and talk to me. I'm very keen to talk to operators because people are starting to use ILMP now, so you may see these packets going across your network. We have some work planned for the future. What I've shown you is assistance at the network level for the transport layer to do addressing management for multipath, and we're looking at what we might be able to do for assisting with congestion control. Congestion control is still best done at the transport layer, end to end, but it might be something we can help with. We're also working on integrating DNS. These experiments weren't done with DNS, they were just done with a Tetra host entry, so in the host file, to make a self-contained experiment. And you can even play around with the code. There's an update version of the code, FreeBSD 14.3, so pretty much up to date. You can grab that from the website and have a play with it. Thank you very much for your attention.